Section 1.7. If you have a book, please open. If you have. So what you have is
What's section that they're assigning?
1.7.
Oh.
Yes. Oh, yeah. I said, what number does he have?
You can't say girl. What time you want to see? See, that's why I can't just watch the game. I just don't That's all. Chris, you
All right. So everybody can see this? You guys can see this? It's this thing is in the way?
No, not yet.
Okay. So what you're seeing here is you have what you're interested, your goal is to understand relative motion of particle P. Okay? And the context is very relevant. So what you have is, you have this moving frame. This moving frame, you can think about an airplane, you can think about a spacecraft that's moving. What is a frame? How do you connect frame and body? Aircraft, spacecraft. Why do I say frame? Why do I interchange frame and spacecraft?
Why do you say what, Doctor?
Why do I interchange frame and spacecraft or frame and aircraft? See, let me suggest something. Don't take notes. Take a picture if you have cameras.
Okay.
Or one of you take the picture and post it for everyone on Slack.
Because you can watch it again.
Huh? You can watch it again, but there is no need to take notes. Notes, I think you'll get lost. You cannot concentrate and take the notes at the same time. So don't take notes. If you want to make notes, just take a picture and go back and do the notes. It will take you hardly 10 minutes. It really will take you 10 minutes if you just look at your pictures and try to make your notes. Okay, so don't take notes and don't get distracted with cell phones. Okay. So what you see here is, this is the inertial frame. Alright? And this is the moving frame. When you talk about frame and spacecraft, frame and aircraft, why do I interchange? If you want to understand a system or something which is moving in a system, we attach a frame to that. And this frame is attachable only to a rigid body. In a plane, is anything changing? It's practically a rigid body, except if you think about the ailerons or the rudder, it's a rigid body, right? So if you attach a frame to it, the frame itself is attached, it's not moving. Only if you can think of the frame as a plane. You see it? The frame as spacecraft. Right? If I have this plane, if I attach this frame, right? You have this, and next you have rudder, right? So if I attach this frame, you define your yaw action about what axis?
The x-axis.
X-axis?
Define your what?
Yaw.
Oh.
Is this yaw?
No, it's pitch.
That's pitch, right? So it's about y-axis. The yaw is about z-axis.
Oh, yes. Oh, yeah.
Z-axis, right? Yaw is about z-axis. It's about something. The rotational movement is about something. It's not in something. The translational movement is in a particular direction. It's in x-axis or in y-axis, in z-axis. Rotational movement is about a particular axis. So yaw axis is z-axis. What is roll axis? Y-axis is roll axis. X-axis is pitch axis. Right? So that is how you define rotational motion. So if I define this, see, if I have this plane, once I attach this frame, right?
Bro.
Damn, I read my pen.
Get back. Oh, man. You see it. This was good though. And the wings.
So once a frame is attached, the body itself is irrelevant actually. You see what I'm saying? So you have to, whenever you think about this frame, this coordinate system, it actually is the physical system itself. You have to imagine the physical system itself. So you can define all motion with respect to, this is the measurement system for measuring system for rotational and translational motion. So translational motion is about what axis for a plane? It's mostly about either x or y axis. Right? It's not much about z axis. Although you can, if it's a helicopter, it can do that. But most aircrafts will either go in x or y direction. Right? But in spacecraft, it is not the case. Spacecraft, it can go this.
Yeah, 6 degrees off.
Right? It has 6 degrees. So the importance of this frame is, you have to visualize an aircraft or a spacecraft attached to that. Okay? When we say moving frame, the aircraft itself is moving, or the spacecraft itself is moving. Alright? This is your point of interest. this is what you are trying to understand the motion of this particle. This is a particle. Now, what we have defined here is, we cannot, if it is kinematics, yes.
When you say that particle,
Mhm.
you're not saying that itself is the object. That's just a point on the object, like a point on the plane. Or what is that P?
That's a point of interest. For example, in an aircraft, this point of interest could be aircraft itself,
Okay.
or it could be a person in an aircraft. Okay.
And in our case, it is.
Hmm?
In our case, is it the object itself, or is it a point on the object?
Just for now, forget about. Don't make it specific. Just understand. You are interested in studying the motion of this particle. Okay. And this particle, the position of this particle is defined, the absolute position. When I say absolute, it has to be with respect to an inertial frame. Right? This P R is the absolute position. And it's defined with respect to inertial frame. R relative is the relative position defined in moving frame. You get that? It's fairly simple, right? R relative is relative position defined in moving frame. This position.
Okay.
Okay. This is and R naught is the position of moving frame with respect to inertial frame. Right?
So, what's the difference? Okay, so first R.
First R is the absolute position of
P.
the P.
Okay.
R relative is the relative position of P, or the position of P in the
Moving frame.
moving frame.
And then.
R naught is position of the moving frame itself, the origin of moving frame. So you think about aircraft is moving, right? There's a point on aircraft which is this. R naught, position of moving frame, position of the aircraft itself, okay, or position of the spacecraft itself.
Okay, I see what you're saying. I'm getting it.
And this is, let's say, your position in the aircraft. If you are moving around, then this is that.
Okay.
Right? If you have a device on you which will tell you your absolute position, if your GPS is working inside the plane,
Yeah.
it will tell you absolute position with respect to this frame, regardless of where you are in the aircraft.
With respect to the moving frame.
Not with respect to with respect to the inertial frame.
If you have the GPS.
If you have a GPS, right? GPS will give you absolute position. That is this position.
Okay.
Okay.
Okay? So if you have a GPS sensor on a plane, that will give you
Got the position. Okay.
wherever that GPS sensor is in the cockpit. This origin is that O. You understand?
Okay. And is there an example for the GPS with R relative?
R relative is you don't use GPS. You use a localization system. Alright?
That's what I was at. Oh, it's really back there.
Now when we say understanding the motion, we want to understand its position and velocity. Right? So you have R is equal to R naught plus R relative. Right? You agree with this? So R is this plus this. This is just vector. Okay, vector 9. Now, how do you define R relative? R relative is x I plus y j plus k, sorry, z k. Okay.
Dr. Sunday,
Hmm.
just before we proceed, that the R vector starting off that equation, that is the same R from down there, the absolute position, right?
Which one? This one?
That R is absolute position.
That's this R.
Yes.
That's absolute position. Yes.
Okay.
So the absolute position is equal to absolute position of. This is the absolute position. You have to be careful. Absolute position of P, of particle P. Okay. That's the reason I've written goal is to understand relative motion of particle P. That's very, very important. Again, this is relative position, same, of particle P. This is relative position of origin. R0 is the relative, is the absolute position of origin. Got it?
Yes.
Okay. So you have this. Now recall the derivative of any vector A, dA by dt, is expressed as dA by dt. This is relative or local plus cap omega cross with A. Okay. So what I do is I use this A circle dot plus omega cross with A. Okay. So don't be confused with this notation. It means the absolute position of any vector A is equal to the local derivative of that vector A plus, this just means the derivative of the moving frame. Okay. So we'll try to apply this. Now what is d r over dt? dr over dt is dt, don't hang on just a minute. Right? dr over dt, I have just taken the derivative on the right hand side. Nothing confusing over there. This is, I can write this as R0 dot plus R relative dot.
Now that's what you just wrote is separate from what you have boxed, right?
Yes. Alright, this is clear. This is the absolute position of the derivative of the absolute position of R is equal to derivative of the origin plus the relative derivative of the relative position. Just look at this and just look at this. I've done nothing. I've just taken derivative. Now you apply this. Apply box. Okay, R dot is equal to R not circle dot. Okay, plus omega, cap omega crossed with R. Okay, plus you have to apply the same thing for R relative circle dot plus omega cross with
Where did that come from?
Hmm?
Where did that come from?
this is this. This is this. For any vector r dot. Okay, the derivative. We are taking the derivative. This is the absolute derivative
The bar.
of r. Okay, so if you are see the absolute derivative, if you know the absolute position, you can always calculate the absolute velocities.
So our capital A circle dot, that's absolute derivative.
This is the absolute derivative. This is the local derivative. And this is the, again, look back in this. So if this was A, or this R was A, this just means that if you have something on your hand again, you can just simply calculate the absolute velocity of that. You understand? In most cases, that doesn't happen. You have to have a relative understanding. You may be able to calculate the even with sun, even with Earth and spacecraft, what is happening? This Earth does not have this frame. You realize? Earth has this frame, right? If you attach a frame to Earth, that is this frame. Actually, the rotating is this frame. This frame is an imagined frame. If you attach a frame to Earth, it is this frame. It will actually rotate, right? What you are understanding is this is your spacecraft, or this is your moon. You are understanding you know the relative position of moon in the moving frame. You know where the moon is right now, but you are moving. You cannot apply Newton's laws to that. You cannot apply Newton's laws to that.
And so what would be the inertial frame?
The inertial frame is a frame which is attached to Earth, but it is not rotating with Earth.
Okay.
It's only, so your inertial frame only does this.
Okay. And then
You got it?
moving frame would be doing.
Moving frame will be always doing that and then also revolving.
So like the Earth and the moon.
Huh?
Wait, the moon doesn't revolve, the moon stays still, right?
Moon also revolves.
So the
Moon rotates, moon revolves. But the period is such that we always see only one phase.
So, is the moon its own separate moving frame too, or is part of the moving frame?
Right now, forget about the moon. This is like moon. Okay, we are only interested in when I say this P is moon. A particle does not have rotational motion. Yes. A particle, rotational motion for a particle, is it relevant? What do you mean by a particle? A point. Is rotational motion relevant for a point? It doesn't mean anything, right? So when we are doing this, we are only interested in the position of that particle. So this particle means that it is, we are not really interested in, right now, we are not really interested in the how the particle is rotating, because particle has no rotation. Okay? Yes?
Okay, so the relationship between those two, so the capital A vector with the dot, what is that? You said that's what?
This one?
Yes, what's that called?
This is for any vector.
Okay,
For
so
any vector, now recall, for any vector, A. Okay?
okay,
So this is separate.
right, and then you're basically
If you want to take the derivative, this is how you take the derivative.
okay, and then you're plugging that in to our vector now.
Right, now we have this, right? now what we did was we just took the derivative of this.
Okay, so
Yeah.
our R dot 0 is there, is that capital A under, okay,
This one?
yes.
No.
So then where did that come from? You, at the bottom, in
This,
the,
you see this?
right,
So this is there, right?
right,
So I have, this is just another way of writing this. This and this are the same.
right,
Now I'll take the derivative of this
okay,
here. This is one vector. These are two separate vectors.
okay.
You realize that?
Right, but what I'm trying to understand is why we added that first one to the omega times.
That's what we said. For any vector A, the derivative A dot is this. If you express it as local derivative plus,
And see, that's why I'm trying to say that R dot, that one right there at the bottom, not that one. No, the first one, that one is our capital A, of the, yeah.
right. So this is this.
Oh, yeah, that's what I was
This is
asking.
this.
Okay.
Yes. Again, for this thing, you have this plus this.
Right, okay,
Got it?
yes.
All right.
So will open dot over R the same thing as open dot over A?
Circle dot.
Yes.
Yeah.
This and this.
No.
This
And,
and.
and R with the circle.
Right.
Yes.
That's the same thing.
That's the same thing. It's not the same thing, same thing. This is for any vector. Okay. But this is something specific. What is R naught?
R naught is the
Relative position of this.
moving
Right. It's the position of moving frame. Yeah, not relative, but the position of moving frame. So if you take the derivative of position of moving frame, this is how you apply it. Okay. Now what you do is you figure out whether this is relevant. Okay. See, this means what? The local derivative, alright, of this, right? That local means it is expressed. It is expressed in this frame. Correct? Does this apply?
Does the omega apply to the velocity of movement?
Right. The omega is the velocity of, is the angular velocity of inertial frame.
I thought it hurt. Well,
Because R is expressed in inertial frame. This is expressed in inertial frame, right?
No, it doesn't have a value.
Huh?
You said it doesn't have a value?
In omega, cap omega is 0.
yeah, because it's translational, right? Inertial
No,
frame
this
is
is fixed.
yes. Okay.
If it is fixed, it does not have, it doesn't rotate. Okay? So this component is 0.
But is it fixed or is it just translational?
This inertial frame is fixed. This, if I do this, it means it is fixed.
Okay.
The frame is fixed. This is moving. This frame is doing all this and also moving.
Well, okay, without the line saying that it's fixed, that could be translational.
This one, when you talk about inertial frame, it is mostly fixed. You can have an inertial frame with a constant velocity, but that is very rare. Especially when you talk about space mechanics. Okay, nothing in space is just translated. It is always rotating. Okay.
And why did you draw that arrow through and say 0?
Because this omega, what is omega? Cap omega. This is angular velocity
Oh. Okay.
of frame. Okay. So this omega will apply to this frame. Because this is fixed, that omega is 0. Okay? But this is not the case for the second one. This omega here is this moving frame, is it moving with respect to this frame? Does it have angular velocity?
Yes.
Yes. So this stays as it is.
So what about for the point P? Do you add that in there?
This is for the point P.
That'll make it cross A.
But doesn't, so,
This is the absolute velocity. This is the velocity of point P itself. Because what is an R? R is the position of point P. You get it? This relative is the relative velocity of point P.
so we're going to third part of the equation for the part P that's not rotating because it's a point.
Yes. The point P itself cannot rotate because it's a particle. Okay? But the frame in which this is expressed could be rotating. Just like that. Okay?
Okay, so the first part is for the inertial frame, second part is for the moving frame, and what about for the actual point?
This is the point. This takes care of translational motion of point in the relative frame. You see it?
Yeah, I see that. I'm just thinking there should be a third part for the point P.
If the
where
point
it's
is, if the particle becomes a body itself, if orientation is important, then it becomes, here we are talking point P, especially in spacecraft, it's a point mass. It doesn't have, we always study that as a remember the assumption I gave you, what were the three, I gave you two assumptions actually. M1 is much greater than M2. The second one is spherically homogeneous. The particle we are studying is spherically homogeneous. Spherically homogeneous can always be considered as a point. Point with the mass concentrated at that point. Okay? So here this one doesn't have any rotational motion. The point P doesn't have any rotational motion. Now this is the velocity. So here V, what you have done is V is V naught plus so this is V naught plus this is d over dt of R naught. Okay. So you can say this is V naught plus V relative plus omega crossed with R relative. Okay, is this clear? How did we get that? You lost again? Alright, let me complete this and then we'll discuss. Okay. Now acceleration okay. So this would be alright, can you tell me how do we solve this? Just go back to this and apply and tell me. It is, for the first one it is V naught circle dot plus omega crossed with V dot. Okay? This is the first one. Plus V relative plus omega, circle dot plus omega cross with V relative. You agree? Plus d over dt, this is local, okay? Omega cross with R relative, right? Plus omega cross with
I got lost on the second line.
this one.
Yeah.
What happened here? Does this make better sense? This itself is a vector, right? I have to take the local derivative, which is this, plus omega crossed with the vector itself.
So what is
Oh, okay, so we're treating the omega cross R relative.
As a one vector. Right.
Gotcha.
Okay, if I just call this, let's say if I call this small omega, alright, this would have been omega circle dot plus omega cross with,
Okay, gotcha.
right? I have to split this open again. Let's see what is relevant, what is not relevant. Is this relevant?
No.
This again goes to 0. See again, if you look at what does BO or RO is. RO is the position of origin. Origin itself is a particle, and particle doesn't have rotation. If you look at it the other way. So here the reason we cancel this is because this R0, this actually is R0, right? I missed that. That's R0. R0 doesn't have any rotation.
So the origin is a particle as well as the particle.
Yes. Origin is origin. Okay. The origin is itself is not. It doesn't have any rotational motion. Rotational motion doesn't have any significance. Okay. So that is the reason this omega, this component is. So now what we have here is acceleration is equal to this plus right v, that is a relative, right, plus omega crossed with v relative. So this one, what happens is I wrote this, right, because I want to take the product rule here. Just apply to cross product. This will be omega cross with v relative minus omega cross with r relative plus omega cross with omega cross with r relative.
Would you subtract?
Hmm?
Would you subtract?
So what I've done here is, this is, think about this as A cross B. Alright? D over dt of A cross B is what? A cross with B minus, because cross product is anti-commutative. cross with but actually it's the other way around. A cross with B. Yeah. Got it? So I have A cross with B. So from B is R relative. R relative becomes V relative. Right? If you take the derivative. Minus derivative of A cross with R. Okay, so this is actually A so I can write this as plus R relative cross with alpha plus omega cross with omega cross with. So this what I've done here is omega circle dot is generally alpha. Alpha is angular acceleration. Just like A is linear acceleration, alpha is angular acceleration. Okay. If I cross this, if I do this alpha cross with the R relative, right? What happens if I A cross B? You should also know that A cross B is what? Minus B cross A.
Where'd you use that identity? Where'd you use that identity?
Here. So it was minus omega circle cross R relative, right? I switched it. Got R relative crossed it. Alpha. This is actually just take it as omega dot cross with R. I'll explain to you why this is the case.
Is that REL at the end too? The very last R.
Right, it's REL. Okay. So this, see what this defines is, do we know anything more than acceleration?
Anything else?
Yeah.
Position?
Yeah. So you have position, velocity and acceleration. We don't know any quantity which will give us change in acceleration. We don't know change in what change in acceleration means. You understand? Is there a change in acceleration? Can acceleration change?
Yeah.
That is acceleration.
Because
And, you know,
so there is no change in acceleration. We don't know that quantity. Although mathematically you can express, you can take a derivative of this as well, right? It will be some other quantity, but we don't know what that quantity means. We don't understand that physics also. So we stop here. Yes, that's all. So this is important. Hang on. Where are you going?
Why did you change it to 5?
Huh?
Why did you change it?
Hang on. Thomas, hang on. Don't just leave. See, if you leave, you'll not digest the last part.
So for omega, why did you change that to a positive?
I'll tell you that. I'll explain to you why I did that. But for now, just take it. Okay? Take a picture. What you'll be required to do is, if I give you a problem, okay? Now, so I'll not give you a very direct problem, okay? You may be given this and asked to find this.
The area right there.
Yeah. Now, you may be given the relative position. Find out. And you'll not be given the formulas. You have to remember this. And you have to understand how to apply this. See, all this should make mathematical sense. But it also should make physical sense. Physical sense. Why? Mathematical sense. Does it make mathematical sense? Kind of. Huh?
Couple more times.
Couple of more times you do it, it'll make mathematical sense. But physical sense, when I say physical sense, math will not tell you that this is 0.
It explains why that's not the book.
Not in the book book is also fine. Book will only tell you that for that particular example, it will tell you this is 0. This is 0 for only this particular example. And that is where you have to think. See, education is not about teaching you about aerospace engineering or making you an aerospace engineer. Education is about giving you the ability to think. If you cannot think for yourself, then there is no point in just being able to do this. In your context, you have to apply it. This, if this is not making sense to you, does this make sense to you? Why this is 0?
Oh,
Micah?
Yeah.
John Lewis? Why this is 0?
Because the position of the industrial frame is fixed, it doesn't move compared to the particle in the moving frame.
And it's not
Yes, so this frame if this applies to this frame, right, and this is not moving. If I just gave you 2 moving frames, all this will still apply. Did we apply Newton's laws here?
No.
Did we apply Newton's law?
It's an argument. You can't apply Newton's laws in
On space frame,
Why did we apply Newton's laws?
because you're not taking into account what caused the movement.
Right. The cause of the motion is not relevant. The force is not relevant. So here there is no scope for Newton's law. And the question was, we were trying to understand the relative motion of particle P without really worrying about what is causing it. The cause of the motion is not mentioned here. Unless the cause of the motion is, and this is what this is. If somebody asks you what is kinematics, one, you have to be able to define. At the same time, you should be able to understand this is kinematics. This is all kinematics. You understand? So kinematics is what? The mathematics of physics. The mathematics of dynamics. When you are doing kinematics, are you doing physics?
Yes.
You're probably not doing physics. Whereas, what physics laws did I apply?
All that.
It's all math.
I got a question. So, R dot 0, why is that not 0?
Which one?
R dot.
This one?
No, that one.
This one?
Yeah, why is that not 0?
Why is this not 0? Yes. Can somebody answer? Why is this not 0?
Well, that one's not the angular velocity. The angular velocity was what made that one the other one 0.
Because it has a
What is the moving frame? That's all.
So this frame when I say it's moving, it's not just if it was, you're right. See, here's a valid question. So what he's asking is, if this frame was just rotating, Assume this frame was just rotating. It didn't have any translational motion with respect to this inertial frame. Would that be zero?
Yes.
See, that is where your physics, that is when you understand now? This frame is actually translating and also rotating. Rotational part,
It's the satellite.
so when this gives this point, this relates to only the point, right? The origin. This is strictly the motion of the origin. Motion of the origin. Origin is what? A particle. When we talk about a particle, it has no rotation. That is the reason this is zero. Now this is what the relative position of particle P, right? But also the frame comes into play. This frame. See, because what happens is, if this frame rotates, right? The particle may be there only, you may be sitting there only, right? But if you're facing north and you're sitting there, the plane moves, plane rotates, your direction will change, right? If your position was fixed with respect to this frame, what would happen? This would be zero. You understand? If you are not allowed to move in the plane, this quantity would be zero. Got it? If this frame was also inertial frame, this quantity would be zero. You getting it? So that is how you have to interpret. So that condition will be just given to you, and you have to apply it in your mathematics or in your physics. Alright? Alright. Thank you. John Lewis, you are free to go.